I'll share my slide first.
Yeah.
So, would you be able to see my slide? Hello?
It is visible, sir.
Okay, all right. Very good morning, one and all present here. Thank you very much for your kind introduction about me. And it's my pleasure and privilege to be part of this event. And of course, in today's topic, which would be on tissue engineering and a hope for donor substitute. So I designed my slide in such a way that the fundamentals importance of tissue engineering will be known to the students because they are young minds at the moment. So when they have a future career, especially they want to pursue in tissue engineering, which is one of the future and the most booming field. All right, so I designed in such a way very simple and very fundamental informations, which definitely it will be useful for the students to pursue their research career if they are interested in. Okay, so of course with that a little bit of introduction, why do we need organ donations? As you can see that, so this is just statistical information, rough information which I've extracted from the Google. You can see almost this, even though the information is a bit old, but still it is relevant. So as you can see, every year the 4 lakhs people are dying because of insufficient or unavailability of the organs. Okay, perhaps the nature of the organs could vary from person to person. Of course, the reason could be many. Maybe could be a genetic disorder, or could be from accident or trauma, or or due to the age. Okay, or any specific genetic diseases. That many diseases contribute for the requirement of organs. But at the moment, we every year, as you can see, the numbers of requirements of patients, depending on the donor, is keep on increasing, but the donor is keep reducing it. All right, so as you can see, the manifolds are keep trending increases, even though as the last 2 years we have good news about there is a good amount of awareness spread among the peoples who are willing to donate it after, especially for any brain deaths and other the unpleasant incident happen. So they're quite that mainly due to the education and awareness created by the respective countries. So which is a good sign. So I don't want to restrict particularly to the India. It is also applicable all over the world. But when compared to other parts of the world, they have certain amount of the information and awareness. But we do have a lot of populations. But accordingly, our requirement of organ is also going to be higher. All right. So in that case, as you can see that there is every year there will be a tremendous increase of the organ. The people are depending on the organ, right? So in line with that, so is there any opportunity? As you can see that if anybody wants an organ, it should be dependent on others, isn't it? But of course not. There are certain conditions, so it depends on the organ, the people can donate. Even our own sibling, of course, if any organs which is quite good functioning, and also still there is a stigma on in our society. So the requirement is keep on increasing in every year, but the amount of receiver, the amount of donor is going to be, it's not catering the requirement at the moment. So in conjunction with that, there is a field called regenerative medicine, where the ultimate aim is to regenerate an organ artificially in X vivo condition and can be transplanted into the person. So in some extent, if an organ can be developed, which can fulfill the requirement, if not cater everybody, but at least it can give support for the dependency on the organ donations. So it's not a new term. As you can see, the regenerative medicine is not a new term. It's there in 1970s. You can't believe that, isn't it? So it's there since 1970s, but every decade it keep on improving its advancement of technology. It keep on increasing, advancement, and we've reached certain stage at the moment. At least, we had a good embark or good hope on the tissue engineering, where in future certainly we're going to replace there a complete organ which no longer dependency on any other person. Okay, so it is nothing but, as you can see, the tissue engineering is a part of the regenerative medicine. In most of the textbooks, sometimes they interchangeably use the term. So one of the elements of the regenerative medicine is going to be a tissue engineering. As the name sounds, tissue engineering, which means you're going to engineer the tissue artificially. So what do you need for that artificial regeneration? You need 3 elements we're going to see in the next slide. So when you look at the component, the curriculum of that particular tissue engineering field, it is a combination of an engineering field and biological field. So ultimately, it is going to helpful for the development organ and either to partially replace or fully replace or improve the function of the organ. So that is the main objective of it. So as you can see here, the tissue engineering triad. So the tissue engineering triad is nothing but tri means 3, isn't it? So the entire concept depends on the 3 important elements. The first one is going to be a cells, obviously. Without cells, nothing is possible. It's the fundamental unit of life. So the cell, another one is going to be the biomaterial, and third one is going to be the signaling molecules. Okay, so this is very important, especially when you have your cells externally. You need some stimulus to retain it, especially for differentiation purpose. If you want to differentiate into chondrocyte cells or bone or osteocyte cells or skin cells or heart cell myocytes, whatever it is. So the signaling molecule is an important factor, one among the triad, which is going to be helpful for the differentiating the cells into the particular type of cells. This is a simple schematic representation for better understanding. So again, this is another schematic and representation of tissue engineering. How does it work? It is going to be quite similar. You might have encountered about animal tissue cultures or cell tissue culture. Even I've gone through your curriculum, which is there some extent of studies on animal tissue culture. So the mechanism is quite be the same. The principle is going to be the same. So you're going to ultimately going to depend on tissue culture work. So what extra moiety is going to be involved in this in the session is going to be then a scaffold. Scaffold is nothing but as an extra element. It gives a three-dimensional support, especially to give cells to spread on the scaffold material to grow on it. So once you grow on it, of course, it will give a shape and architecture for that construct that which can be translated into the patient. Okay, so the image looks sound. Oh, you're going to harvest it and culture it and transfer it and put it back. But there are lots of practical difficulties which stops for us moving forward since 3 or 4 decades ago. So anyway, so due to the fundamental sound knowledge developing every year, so the improvement of application is quite vast at the moment. So still a lot of research is going on. So certainly there is no doubt, and one day there will be a complete reorganization or complete generation of an organ externally. Okay, some of the pictures I posted here, which is artificially synthesized from the renowned publications. So as you can see that this is just a bladder which is artificially synthesized, and this is a trachea. As you can see, there's another one which is heart, which is again crafted by 3D printing technology. Another one earlobe, and as you can see, there's another trachea. This is also artificially synthesized. You can't believe you don't have to depend on any donor to wait. Nobody's going to donate it if they are alive, isn't it? So there are plenty of opportunities with the help of the tissue engineering to regenerate an organ. Finally, you can look at that. It could be like a candy, doesn't it? So it's not a candy; it is a kidney. So one of the reputed university from United States, they've developed this, and so you can see there is a secretion of separation of urine components. So they tried it. It's a model, but it gives a hope that there will be a possibility of complete regeneration of kidney. All right, so let's look at the cells. What are the cells? As I said, in the triad, one of the important component is going to be the cells. This is the first element of the triad. So cell is the fundamental unit of our living being, or fundamental unit of any tissues, isn't it? So the cells is important. So obviously the choice of the cells is purely depend on the type of organ which you want to develop. So I've listed here, as you can see, the fibroblasts, as everybody knows about it. It is quite responsible for the generation of skin. Similarly, if you want to regenerate a bone, osteocytes. And if you want to do for the chondros, the cartilage materials, which is the chondrocytes, and of course, and proportionally, you can see myocytes for heart, okay, and adipocytes for fat tissues and other stuff. So obviously the type of cells which you're going to generate, it is very, very important. Okay, so let's move on to this. What are the types of cells which is currently being used in tissue engineering? As I've listed here, this could be fundamental, but it's very, very important. So the first one is going to be autologous. Auto means, as you know, self, isn't it? Everybody knows about it. So same person. For instance, if I feel that I can donate, I can take a portion of a skin and can be preserved for quite some time, and it can be recycled. As you can see, even nowadays the stem cells, when a baby born, nowadays the technology is a bit advanced. They can also take up their own umbilical cord. The stem cells they can preserve for many years, for perhaps more than 20 or 30 years, so that if the same person undergoes some specific diseases, that same person's stem cells can be utilized for the regeneration. That's a quite example. Similarly, so any tissues which is taken out from the same person can be harvested, can be organized or developed externally, and then it can be transplanted later. So another one is going to be allogenic from same species, which means I get an organ from a different person. Okay, so get a donor, maybe a sample of a biopsy of cells or tissues. You can proliferate it, and with the help of the tissue engineering, you can develop it and you can transplant it. Right, that's called allogenic, which is from same person, which means same species from other person. Xenogenic means, of course, different species, perhaps maybe from animals. Okay, if dependence, though, you need to do that. Isogenic means it is iso means same. Of course, it's going to be a twin brothers or twin sisters. Right, so the most probably the organs cells will be more compatible and compatible and convenient for the cells to be proliferate without any or the limited or minimum rejection of cells. And primary cells, as you see, is one of the technique, because normally if you take a cells or an organ or tissue, just mince it and extract it. So the moment when you get the first culture of cell, we call it as primary cells, which inherit the property of the organ, so which could be beneficial, right? So secondary cells, of course, secondary cells, when you passage few times, okay, so when you keep on passaging, so that you no longer every time depend on a primary cells. You no longer take a biopsy every time from a person and store it for the purpose. In that case, you can keep passaging in, proliferating, and keep preserving. So whenever you want, you can take that. Okay, so that's called secondary cells. And stem cells. Stem cells is one of the most boom for the tissue engineering applications. You could have seen many advertisements, even from umbilical cord stem cells preservation, especially during the delivery, and even many cosmeceuticals. So they come up with that, but the validity of the information is still to be ascertained. But there are good amount of outcomes has already been there for the stem cell treatment, especially for the regeneration or malfunction or the revival of the malfunction of an organ. It could be either completely or partially. All right. Another one, this is a schematic representation, as you can see on your right top. So this is a stem cell. As everybody knows, stem cells is cells which can differentiate into any type of cells. So based on the signaling molecules. As based on the potency, it has been further classified as multipotent and a pluripotent. As you can see from the multipotent, there are neural stem cells and MSCs and HSCs and other stuff, which is quite this another ocean of information. You can go through it. A lot of application which currently is going on in a regenerative medicine. So let's move on to the pluripotent stem cells. Pluripotent means it's can able to generate any type of cells, which is a naive cell which has ability to any type of cells. So basically, embryonic stem cells. Embryonic stem cells is the boom. Again, it's a boom for the regenerative medicine. As you can see, I already mentioned umbilical cord stem cells. Another, the most advanced and the most, most preferred and most advanced, and it currently is being used. Most of the research for the umbilical cord stem cells, because most of the stem cells, the resources they want to from the same person, and can be more beneficial. And of course, it is going to be a very naive, and it can be triggered and differentiated into any form of cells in later. Induced pluripotent stem cells, another one. Which is currently very hot topic. As you can see, majority of the genetic diseases, which is effectively, is effectively can be treated by the iPSC. There's a lot of research is going on. Even some the clinical trials is also underwent for one of the genetic diseases. One of the recent of one of the conference which I've attended, which really is worthful information that iPSCs are the next upcoming boom or reliable source of our organ replacements. Okay, this is another one which is a simple schematic representation, as you can see, but as I mentioned already, it may sound simple. You can just take out and mince it and just passage it and store it, but behind that there's a lot of science is going on. Okay, as I mentioned in the briefing slide, I told you it's there since from 1970s, but it is picked up in only 1980s, isn't it? So almost, when you look at it, it's almost more than nearly 4 decades. So by now we might have completely regenerated an organ, isn't it? But the thing is, there's a lot of hidden science behind it. Our physiology is also one of the most complex systems to be understand. Okay, so of course, each and every stage, every decade, we have a very good improvement, and maybe still we long, if not a long way, at least we some extent of way to be proceeded further to get complete achievements. So this is just a representation. As you can see, this is for embryonic stem cells from the cells, and this is just for different source of cells. If you want brain cells, neuron cells, preferably primary cells, you just harvest the organ, and of course do the procedure to lyse it and extract your cells and just cultivate it. So this is okay. Let us move on to the second element of a triad, which is a scaffold material. Okay, so this is itself a different field. The scaffold, as you can see, in a simple way of understanding. What do you mean by scaffold? Scaffold is nothing but a simple any structure which gives a support. I'll give you an example. If you want to construct a building, as you all know, what they do it. They construct the scaffold first. Scaffold is nothing but, in Tamil we call it as charam, right? So the people will stand on it and sit on it and to construct a building, isn't it? So over a period of time, when you constructed the building, obviously you need to remove the scaffold, isn't it? So there is no point of keep retaining the scaffold even after you construct your building. So it doesn't fulfill the requirement. So upon completion, it should be shed off, isn't it? So the same material here, the same principle here. Scaffold is a supporting material in which the cells will seed it and will grow on it, proliferate it, and over a period of time, it should be degraded by itself. So when it gets degraded, there will be a void space will be generated, isn't it? But ultimately, that will be fulfilled by the cells as well as the extracellular matrix, which is secreted by the cells. So it is one of the important elements in the tissue engineering triad. So ultimately, it needs to, as you can see, that it should be conducive. It should give a conducive environment, okay, and it should allow the cells to proliferate it, and it should have proper mechanical properties. Very, very important. The mechanical property decides and defines the usage of your scaffold. All right, and also it will define efficiency of a product. Okay, so some of the and of course it should be less immunogenic. If it is good to have less immunogenic, because we can't in nature, we can't assure that any forest, we can't assure that our immune system cannot detect it. So even though we claim it is non-immunogenic, but there are certain extent of immunogenic will be there. So it is good if we have complete devoid of immunogenic reaction. If not, it's a minimum reaction is required. Okay, so that's one of the fulfillments for the scaffold material. I've given here, as I mentioned before, these are the scaffold material which can be molded according to our requirements. As you can see, this picture, which is quite near to the bone head. Okay, so it's a thigh bone head. So it was molded to the shape of the bone. So the cells will be seated on it, cells will grow on it, and over a period of time, this material, this will slowly go off. So this is completely replaced by the mineralization process by the osteocytes. Okay, so this is, but for always that there will be a quite long time it will take, maybe sometimes it may take 6 months and even more than that for to completely replace that, but certainly one day it will does. And so as I said, I already highlighted again, it should be biocompatible, which means it should be friendly to that. There should not be any immunogenic reaction. That's called biocompatible, compatible with your system. And biodegradability, so over a period of time it should degrade and get it off. Mechanical property again, so it should be proper mechanical property. For instance, if you use a scaffold for a bone and cartilage, there must be a certain amount of strength, mechanical strength is needed. For instance, if you want to regenerate a cartilage, there must be a flexibility is needed. Where in case if you want to do it for a bone, there will be hardness is needed. If you're using for the scaffold materials for your skin, there must be elasticity is needed. So obviously, based upon your type of requirement, the choice of the biomaterial should be chosen it. Okay. All right. Let's move on to the next one. Again, this is a biomaterial. This is a general term, biomaterial. As you can see, any material which can interact with our biological system, we call it as biomaterials. Okay. So this again, it's a part of the biomaterials are important elements for help us to define or architect the scaffold. It is a large field. It's a large field. It is a separate field where a ocean of informations of choice of biomaterials are there. All right. So this is just for simple understanding the current, the classification of biomaterials. Basically, it's been divided into two major types, which is natural sources and synthetic sources. And there are some semi-synthetic and ceramic sources also available, and which is also effectively used in different types of tissue engineering process. Out of this, natural and synthetic, they have both pros and cons. Okay, let's see about it. So the natural polymers, as I can say, I've given quote an example is a collagen, which is one of the most abundantly used protein. One of the abundantly used protein in the tissue engineering application. Almost is 30% of a body consists of collagen. Okay, so natural polymers, because it's one of the most abundantly utilized in tissue engineering application because of various properties. Okay, so especially the less immunogenic and easy degradable, and also is biocompatible, less immunogenic. Okay, and it can be moldable, and very various of applications on pros of the collagen. And of course, it has its own limitations. As I mentioned, why do we need the nature? As I said, anything which comes from the natural origin, of course, there will be certain levels of compatibility with our physiological system. So any foreign substance, completely foreign substances, then there will be chances of rejection, isn't it? So the main preference is go for the natural origin. As you can see, collagen, which is present, 30% of the collagen which is present in our body, so which is abundantly used biomaterials in the tissue engineering application. As you all know, this is a triple helix structures, and of course, our state is quite familiar for the collagen invention of triple helix, which was invented late in our in CLRA director. So as you can see, there's the different types. And again, so the most abundantly types, as you can see, 28 types. The most abundantly used types would be 1, 2, 3, and 5, and 10. So most importantly, the type 2, which is mainly used for the applications of bone and hard tissue engineering related work. And as you can see, there's a good porosity. Porosity, why do we need a porosity? Porosity means porous. It must have a porous, because the porous will assist the cell to migrate in depth of the scaffold, as well as it will also permeate the nutrients which you are supplying through the medium. It will permeate through the porous and reaches the cells. So the cell will consume the nutrition and will grow on it. Next one is going to be the biodegradability. As I mentioned, over a period of time, it should be degrade and should be, disappear. Compatibility, it should not cause any immunogenic reactions. So it possesses almost every requirements of tissue engineering, but one limitation is poor mechanical properties. So in order to get rid of that, so maybe we need to use in combinations. Let's see another examples of natural, which is also abundantly used, which is a type of a polysaccharides. The chitosan, which you can see that, which is mainly obtained from the hard part of the animals. So the chitosans, which is hard, as you can see, which is the second abundantly available polysaccharide. The first is the cellulose, which is also enormously used in tissue engineering application due to the good efficiency of the mechanical property. Okay, so as I listed here, another example is going to be polyhydroxy acid, which is just synthetic. There's a lot of synthetic materials already available, but I just quoted one example. So PLGA and PGA, polyglycolide and glycolic acids. Okay, so they also use in terms of combinations, it has its own advantages. For instance, the beauty of this synthetic materials are you can mold the shape as you can, and also you can define the oddness. And of course, there are synthetic materials which can be biocompatible, less immunogenic, and it can be biodegradable property as well. So those are the days we only depends on the natural source. But nowadays we can have a good combinations of synthetic and semi-synthetic, and also natural combination could help to achieve our focus. Okay, as I highlighted before, this is a composite. Composite, nothing but it's a combination. So when you use individual polymers, they might have its own pros and own cons. So in order to address the requirement of our object, so we need to have multi-dimensional properties. So that multi-dimensional properties can be achieved with the combination of different materials. As you can see that nowadays, not only the related tissue engineering, any type. So always they try to, even for preservatives, when you do it in a combinations, the efficiency will be more. So similarly here, when you apply for the tissue engineering, you need to look for various parameters. As I mentioned, biodegradability, biocompatibility, and less immunogenic, and mechanical property. So ultimately, if everything is fine, but if it is not able to mold it, then there's a problem, isn't it? There will be a hindrance for us. So now the synthetic and semi-synthetic material gives a way for us to proceed the way what we expected. Okay, this is one of my paper, which is published way back in 2013, which is just a combination of collagen and chitosan scaffold. And with the help of the aloe vera, as you all know, the aloe vera, which is quite commonly used for most of the cosmeceutical purposes, and also in traditional medicine, which has also been used due to its very antioxidant properties, and also it has n numbers of applications. So I've tried it. We've tried it, and successfully we have seen it quite good results, promising results, where the presence of aloe vera could promote the growth of cells, and also it increased the penetration of the cells inside the in depth of the scaffold. So this is another paper of mine which I haven't published yet, so it's in the communication yet. So this is just for cartilage tissue engineering. I've used certain amount of the similar way of collagen and chitosan, and I've used for the trial. I've used for the generation of cartilage material. And I've used the type 2 collagens for the development of the scaffolds. I've used the primary chondrocytes, which I've harvested from the rat chondrocytes. So after seeding it, after 3 months, we have seen there will be a transition of the cartilage development, and which is also we have with an evidence of scanning electron microscope, you can see the noticeable structures of the cartilage or chondrocytes is going to be a spherical shape. As we have observed it retain its shape. As we have used the primary cells, perhaps over a period of time due to the external factors, it may lose its inherent property. But when you see that it retain its important property of its shapeness. This is physiological or morphological structures. And we also see some of the confocal structures, images, which you can see the depth of penetration where the cells is, though we see it at the top, but the penetration we can able to see, this is just we have taken, I think, around a 4th week. Okay, so you can see that it's a good amount of penetration in the presence of aloe vera, which you can see that. And also we can confirm with some of the specific markers, particularly for cartilage, which is collagen markers, and aggregate markers. So as we can see, it is quite predominant in the type 2 collagen secretions. As you can see, it is also further confirmed by the specific immunohistochemistry studies by specific markers. So which shows that there is a secretion of extracellular matrix which is rich in type 2 collagen. Okay, let's take another example of this. Is adopted from one of the journal, where, as everybody knows, the hydrogels. So especially in the pharmaceutical field, we use the hydrogels for drug delivery, isn't it? So it is one of the most efficient and most solid and reliable delivery system. So which also can be used for seeding the cells. So which can load the cells inside. So by using the same method, by calcium chloride method, just you can encapsulate the cells within hydrogel and you can cultivate it. There are studies also been reported which the beads can be administered at the site, and over a period of time the cells can be reach that particular chondrocyte area, and slowly the alginates will be degenerating. So ultimately it's going to be delivering the cells. Okay, this I've just enlisted here the list of techniques to fabricate the scaffold. As I said, biomaterial is an important element. Of course, you need to fabricate it. You need to make a shape which you want it. So that is going to be the ultimate utility of the technique. So there are plenty of methods out there. You can very simple method, solvent casting method, gas forming method. When you keep going on at the last three methods, which is electrospinning method, especially the bioprinting, CAD/CAM method, this is quite advanced, which gives a room for us to design or architecture the shape of the scaffold, which is going to be the boom for us and give a hope for us for the development of an organ. Okay, this is another representation. As you can see, there's a lot of publication, even though it's quite an old one, but you can see there's a lot of different methods. They've used different applications. Just for extra information, I put it here. Let's move on to the 3D bioprinting. I'm going to give a hint, as also you already had a talk, I think, on 27th. I've seen your videos. So they also given a talk on bioprinting. Yes, this is also another emerging field, and similar to the tissue engineering, it is way back, started in 1984. It's not a new term. We might have heard it's a new term, but it's not a new term, but it's there from 1984. So every decade that'll keep on, due to the technology and science improvement, it has come to the stage where it can able to mold the complex structure of an organ. As you can see, yellow, these are the simple, the scaffold materials, but still it has its own shape and architecture. This is very, very important, especially when you go for applications. Still, and it is, again, as I said, even though it's old, but still it is a hot topic. In future, this is the hope, where it's going to give a complete regeneration of organ. But one of the current limitations of the bioprinting can be addressable is maybe you can, for other methods, you may architecture the compounds or architecture the organs which may not have a complex structure. A simple structure can be done, but what happens if it's a complex structure, especially the heart? As you can see, it is a multiple. So when you do the slice of the heart, you can see how complex it is. It's very difficult even to understand, isn't it? So when you develop a complex organ with the help of the bioprinting, that is a success. But still, we long way to go. But the bioprinting is give a hope for us. There will be a possibility in future to generate a complex organ for the regeneration. Okay, let's maybe I would like to touch upon about the perfusion and deceleration. This is another method of to getting a scaffold. Okay, so as you know, we have seen the different techniques. As I also mentioned, one of the CAD/CAM technique we can use to structure the complex organs. But again, we haven't achieved a complete, a complex organ molding happens in 3D printing. But still a way to go. But here, meanwhile, is there any alternative we can address that? Yes. So even though it is not the new one, is also there is quite some time, but it gives another hope, another dimension of hope for the scaffold generation, which leads to the organ regeneration. So as you can see, the first one is going to be the heart, where it is extracted from the cadaver, a person who died it, so that you just remove it. That's called deceleration. So you're going to remove it by perfusion technique or by, you know, some chemical assay method. You can flush out the dead cells. So when you do it, finally you end up with only the cells. It's called decellularize a heart where there is no cells at all, only the extracellular matrix, which is going to act as a scaffold material. Now this materials, now if you're going to use for to inject or seed the cells on top of it, the cells will penetrate into that, and it can revive the entire heart. Okay, so even though it is a proposal, but there are certain extent of success which already been achieved. So you can see that another one, this is a liver organ, okay, which gives a hope. So which can effectively address the current limitations of design of complex organs. Okay, so this is another article which I captured from University of Minnesota from USA. They successfully done it. So they took the rat heart and completely decellularized it, and of course they tried to reanimate or recellularization. So they tried to administer it, and of course they also find over a period of time it's beating. And they got a astonishing invention, or gets stunned by that, but they added the cells on top of it or injected at randomly. But as you know, the heart, only the 30% of the heart is made up of myocytes. The remaining are non-myocytes. Okay, so only the myocytes are responsible for the beating of heart. But this administration, they found it interestingly, the cells penetrate and reach the spot where that beating processes happen. So it gives a hope. But it gives a hope there will be a possibility one point of time there will be complete reanimation of or regeneration of the complex organs. Okay, let's move on to the challenges. As I said, as we all see that it has a potential to regenerate the complete organ or partial organ, and which can replace the donor, but still long way to go. As I mentioned, the first hindrances to choose an ideal scaffold, even though we have there's thousands of papers you can get it by the scaffold, but each requirement of the scaffold will vary from context to context, organ to organ, requirement to requirement. So defining a perfect or appropriate scaffold for the requirement or to address a particular problem still is challenging. Okay, it purely depends upon the biomaterial which you're going to choose it. It must have all the properties. So still it is a potential challenges, but it can be overcome. And again, some of the ethical issues are still pending, especially for stem cells incorporated in the regeneration. And of course, I said the complex organ itself a hindrance, I said. So if it is simple skin regeneration, nothing simple, take a scaffold of collagen, just growth on it. Even you could have seen it. Sometimes you could have read in newspapers that fish skin can be used for the regeneration of skin, especially for burn wounds, which tremendously reduce the scars. Okay, even though the skin regenerate, but there is a leftover scar which gives a negative stigma on the patients. So there are plenty of work is going on. Even there are some of the successful the skin tissue engineering which can be done with the help of the collagen, which can effectively reduce the scar formation. So in this case, that tissue engineering plays a significant role. So it's a hope. So one day there must be the possibility where the complete devoid of chiliosis, which is nothing but some marks, can be get rid of it. And of course, in order to achieve that, in order to completely, as you can see, what we can see, the achievements of tissue engineering, it's like a tip of an iceberg, but there are plenty of challenges and unsuccessful, and it's just submerging under the water. But due to the understanding of science and technology, the time or in future it may may not take in a few years. Maybe it'll take a decades. Okay, but certainly one day the iceberg may flip around, so that the success will be more. Maybe the challenges will be quite less. So I think with that I end my presentation. I would be happy to answer your question. Thank you very much for patient listening. Over to you, sir.
Thank you, sir. Students, any question? Yeah, there is a question, sir. Yeah, there is a question, sir.
Yeah, please go on, sir. I would be happy.
If we create one soul for these things using this 3D printing.
So your voice is a bit echo, so I couldn't hear you.
Yeah. If we create one soul for using these 3D printing.
If we create, could you repeat, sir?
So I think
your voice is a bit echo, so.
Yeah, sir. The thing is, he is asking when you make a material using 3D printing, can we give life to that?
Oh yes. Okay, that's good question. Of course, yes. Of course, yes. So the 3D printing, as you can two-way, as they are using it. For instance, as one of my slide I mentioned about it. Here. So this picture, you can see that this is just a prosthetic. So if you have it, it should be. It is not a regeneration of an organ, but the bioprinting, which it helps to define the complex function of an organ effectively. So if you develop such matter, then you need to have it permanently where it will not help you to regenerate it. But if, for instance, like this cases, or maybe I can go to the first slide, which maybe here. Let's take this. If you generate like this material, which have a provision the cells to penetrate in and proliferate, then certainly yes. So it has a multi-dimensional application of 3D printing. In fact, the 3D printing is not only related to the tissue engineering. It is applicable all across every field. Yeah. Am I answering your question?
I think so, sir.
Yeah.
And sir, I had a question.
Please.
Tissue engineering is something like growing the lizard style. Is it correct?
Growing?
In nature, lizard. Lizard, yeah.
Yes.
When its tail has been cut off, automatically it will grow again.
Okay.
It is something like that, or it is different, sir?
Oh, okay. So that is different. That is a system itself. When the lizard cuts its tail, that's for that nature gave a provisions to divert the predator. So that is different. So the tissue to divert the predator, so that meanwhile that particular lizard will escape. So that is the nature provision. That is not relevant to the tissue engineering. Tissue engineering is just you're going to use your cells to regenerate the entire organ outside of your body in an in vivo or in vivo condition, or sorry, in vitro condition, so that later that can be implanted back into your system.
Okay, sir. Thank you, sir.
Yeah.
Sir, I had a question about scaffold.
Yes, please go on.
So normally in scaffold we can make it like a mold.
Okay.
Because if you want to make a heart shape,
yes.
So there may be interior cavity should be there.
Yes.
So during those conditions, how we are going to make a scaffold, sir? Because the scaffold is going to be play a main role in a generation of tissues or particular organs.
Yes.
So a cavity like such, how it can be generated in scaffold, because the tissue can grow on their own.
Yes.
So how it is going? How it will attain a particular cavity like such as when you're using a scaffold?
Yes, that's a very good question. As I said, one of the limitations, as you can see, the scaffold. See, as you can see in this picture, can you see the pictures?
Yes.
So can you see that the scaffolds are just a supporting material. It gives a 3-dimensional support. If you see the cells on a culture plate, it will grow only on 2-dimensional, which is not that effective. But then the tissue is always in 3 dimensions. So you need to give a support in a 3-dimensional manner. No matter for initial preliminary studies, you can do on any shape. But if you intend to develop an organ or to substitute a part of an organ, then you need to define or you need to architect that scaffold in line with that. So if you want to achieve that, there's a first priority supposed to be on choice of biomaterial. As I said, one of the limitations is still we are looking for the best biomaterials which can address all our requirements. As I said, it might have a good biocompatibility and biodegradability, but poor mechanical property, or sometimes the nature of the biopolymers will not reflect what is in vitro condition. When after implanting, it may not be reflective. So as I said, one of the major limitations is the choice of biomaterial, which is going to be the fundamental requirement for defining a scaffold or architecting the scaffold. So that's the reason we need to go for the composite material, which is a combination of different polymers, which every polymers which have its own pros. Okay, so the cons can be addressed by the pros of another polymer. So certain combination of polymers or biomaterials, certain ratio could address it. But again, we haven't achieved the point yet. We can straight away say, okay, you use this combination, we can address that issue. We haven't attained the age yet. So that's what a lot of researchers keep going. So when there's a lot of information comes about the polymers, especially the biomaterials, then we can certainly achieve the point. But at the moment, it's pure, we haven't attained the stage yet.
Thank you, sir.
Yeah.
So you have told about stem cells during your presentation.
Yes, please go on.
Yes, sir. Stem cells is used for gene therapy or regenerative medicine, sir?
Yes, that's a good question. So the gene therapy is nothing but both are quite. The gene therapy is a different field, but the gene therapy can be used for regenerative medicine. You understand the point? The regenerative medicine is it's a broad term, especially to regenerate a malfunction organ, either partially or fully. Okay, if the malfunction is due to this default or default of a particular gene, then it can be substituted with the specific or the correct gene. So it can go and effectively replace the malfunction or faulty genes, and it can replace the the correct gene, so that it can reverse back. It can reverse back the function of the organ. So in the case, you can use the scaffold material for delivering the genes as well. Yeah, it's quite interlinked. Especially ultimately, the main is to bring back to the normal position of an organ, normal function of an organ. Yeah.
Thank you, sir. Sir, you have told about 3D bioprinting.
Yes, please.
And also you have told about the tissue engineering.
Yes.
Both are similar. If they are different, which is having more advantages?
Oh, okay. As I said, the 3D printing is a different field at all. It is a different field, and the technology is it is a wide application. Even you can see the toys. Not forget about tissue engineering. You can even for designers. Even 2 years back or 3 years back, one of the rumors is come like there's artificial eggs are coming, the artificial rice are coming, which can be generated by the 3D printing, which means it is a technique which can, as we all know, we know the 2D printing, isn't it? When you give a print in a paper, it will print the letters and comes it. It's a 2D printing. 3D printing is nothing but it gives a 3-dimensional pictures or 3-dimensional object. So it is a technology. It's not only limited to the regenerative medicine or tissue engineering. It is applicable for anywhere, even if you want to complex structure of any engineering tools. Okay, that can be used in. But we are utilizing that technology for structuring or architecting the scaffold for the regeneration of an organ. So ultimately, the involvement of the 3D printing here to develop a scaffold material. a particular architecture, a particular shape, especially for complex organ, is very, very important. Okay, so that the polymers the biomaterials which you're using for that, it should be it should be palatable, or it should be more convenient for molding process. At the same time, it should, when you sterilize that scaffold, and you need to seed the cells on top of it, so that it should allow the cells to grow on it and permeate the cells to penetrate into it and proliferate it. So we are merging, as I said, it's an interdisciplinary field. We are utilizing the 3D technology for generation of complex, the complex organ scaffolds. Does it make sense?
Yeah, thank you, sir.
Yeah.
Sir, so you are from Tamil Nadu.
Yes, please.
Here we have a practice like when a child has been born, the umbilical cord has been taken out and kept in a cloth.
Yes.
And it has been stored for a longer period of time.
Yes.
So that that umbilical cord can be used for some therapy in future, sir, which has been stored 10 years back or 20 years back. Still,
Yes.
it will be there in that
Liquid nitrogen.
Yeah, that. So, what is your opinion on that, sir?
Oh, yeah, thank you for raising this question. Even not only in India, even in Malaysia. So during any conferences, stem cell peoples, the particular company will come and give an advertisement, put a booth, and they're promoting it. And in our clusters, there's one expertise from tissue engineering. I mean, especially the stem cell. I ask the same questions as you all say that it can be used. If you preserve our stem cells, it can be used our own requirement. But in practicality, most of the disease or the organ failure which comes, after 50, isn't it? So after 50 years, due to the age or lifestyle and other stuff. Only few people may become much younger, maybe due to the accident or trauma or whatever the case is. Okay, so but when you look at the viability of the stem cell, the potential of the stem cell which has been stored, but from my personal opinion, for 50 years preserving liquid nitrogen, but I'm still personally, this is my personal opinion, but still I have doubt on that. If it is for 20 years, I think some of the papers they mentioned around 22 years around, maybe maximum 25, but 50 years, because most of our lifestyle requirement, organ requirement may be after 50. So before 40, we always be healthy and we don't have that age-related ailments, except the cases of, some rare cases. So what I'm trying to say, the actual requirement of stem cells will be there majority of the time after 40 or 50 ages. Or till then, after 40 years or 50 years, when you revive the stem cells, whether it can be able to address or not, but still, I also don't have the answer for that. But if it can 20 years, yes, it is. That's still a lot of research has to be done. This is my personal opinion. Yeah.
Yes, sir. Thank you, sir.
Yeah.
There is any tissue engineered product available commercially, sir?
So commercially, not yet. From my knowledge, not yet. All are preclinical stage, and they have done experiments in animals, and they are okay, but not yet for as a whole organ, not yet for humans, because as I said, the behavior of cells in vitro is different. The moment when you implant it into it, as I said, our system itself is very complex. We can't predict it. Okay, we can't predict what will happen. But there are certain stem cell researchers they are very successful, as we all know, the Dolly sheep. Everybody knows about it, wasn't it? So that was embryonic stem cell regeneration of the entire cell of a sheep. But we heard about the positive signs, but we don't know the actual outcome. Whether viability, even though we said that organ transplantation, but when you look at that organ transplantation of even a kidney, it could be success for a few years, but how long, the complete data we haven't yet.
Okay, thank you, sir. So you have been in the field of tissue engineering around 5 to 10 years.
Yes.
So what is your opinion about that commercial products? When it will be launched? Because due to the organ transplantation, there are a lot of human trafficking, a lot
Yeah.
of crimes is based on the organ transplantation. So,
Yes.
so what is your opinion regarding the tissue engineering for organ transplant? How long it will take, sir?
Okay. So that's a very good question. Even I think nobody can guess at the moment. But what we can assure that in future, certainly there will be a possibility of complete regeneration of an organ. So for that, we need to have a strong science knowledge, because even a one single cell, we don't know exact 100% of every cell. Okay, there's a complex of system, is the pathways, cells and behavior, how does it triggering mechanism. So it is a long way to go. I think at the moment nobody can assure when are we going to achieve the target which we can able to regenerate an organ. But as you can see, the publications in a preclinical studies, it gives a hope. It may not be very too far away, maybe another 20 decades, 20 years, maybe 2 decades, maybe, because now the progress happening in exponentially. So because of internet, because of technology advancement, so every part of the world, the information what they gain is immediately shared. So now the development happens in exponentially. Maybe might assume maybe maximum of 2 decades could completely could replace dependency on organ, but which is uncertain at the moment, but it can give a hope.
Thank you, sir. So nowadays there is a more focus on individualized therapy, something like gene therapy. The
Yes.
research is widely going over towards the individualization of medicine.
Yes.
So as a pharmacy student, they have studied biotechnology or microbiology,
Yes.
but and the biotechnology higher studies is not their piece of cake.
Mm.
So what is your opinion? What are the scope available in the pharmaceutical biotechnology and how they can grow if they choose biotechnology as a career? Your opinion on that, sir?
Okay, so biotechnology, you mean to say, after the pharmacy, or how was your question?
After the B Farm.
After
So
the
if you see the M Farm biotechnologies compared to genetics or chemistry or analysis, there are less admissions nowadays. People
okay,
are prefer to join over there
okay.
because there is a competition from external also, B Tech or BE.
Okay,
So the people are selecting M Farm biotechnology even though there is a wide scope of research opportunity.
okay.
So just your
Thoughts, is it?
word for that.
Okay, all right. That's a quite tricky question. Um, but what I'm trying to share, the current education system, we no longer stick with the particular specialization. As you can see, even though you might be a pharmaceutics, but when you look at it, the work, it will be interdisciplinary work. And if you say the biotechnology, okay, so you may not be completely dependent on biotechnology alone. You need to have interdisciplinary knowledge and skills. So maybe your field of expertise is going to talk to others, not about your background or not about your degree. So for instance, if you're quite do a research, especially you're good at an opportunity, maybe you would have performed in pharmaceutics, or maybe you'd have biopharmaceutical, or maybe pharmaceutical biotechnology. Either way, you've completed your UG. But when you go for your research, especially in abroad, I'm talking about abroad, so they don't mind about what background you're from. Okay, if we have a knowledge about it, a fundamental knowledge about it, even if it covered in the curriculum, and they can able to train you. So what they are requiring in the research field always, even for PhD or postdoctoral, they don't mind about you need to be quite excellent in that field. The factor which you are interested to gain the knowledge or you thrive to understand, or to push forward yourself to understand the concept and your involvement and hardware, which is going to be the helpful, or which is going to be the driving force in the next generations. So biotechnology, of course, has its own way of advantages, whereas you will be studies a lot of applications oriented and microbiology oriented. Okay, but the thing is, as I say, especially for India, so always the investment for biotechnology is a bit costlier. So, okay, even when the students, when they have fixed the mind, okay, I want to do some biotechnology job, it's maybe difficult for them to get the job related to the field where they're interested in. So one limitations are there, because it will take some time for our countries. Where in terms of pharmaceutics, especially, is I think roughly around nearly 20,000 companies are there. At least some extent, at least even if you take 5% of the companies, they need an R&D, then there is a requirement of pharmaceutics. But here, nowadays, the focus will be having bioproducts. Okay, as you can see, is genetic. As you can see that the gene therapy, gene medicine, even for vaccines, they're good examples of vaccine. So it is a very good opportunity for to venture into the field. So it doesn't mean you need to be biopharmaceutical technology in order to have a vaccine. But as long as if you have some amount of knowledge, which then, of course, the course could be one of the bridge for you to achieve the knowledge. Apologize. So your interest. So the future, anyone can go any field. So they won't. I'm talking about after 10 years. The specialization depends on your research interest. So you can switch, but ultimately, if you're excellent at that, you can go anywhere. So that's. I'm not sure whether I answer your question, but with some extent,
okay,
I tried.
Sir. Okay, sir. Okay, sir. So thank you, sir.
Yep.
Students, any questions?
Sir, good morning, sir.
Morning.
Sir, any in silico study is possible for predicting the biocompatibility or biodegradability in tissue engineering, sir?
Oh, yeah. Currently, the in silico studies for release profile, there's a lot of that, especially the release of scaffolds, especially to deliver the particular neurotransmitters or growth factors, especially to differentiated factors. And also the in silico studies for compositions, composite materials. Yes, there's plenty of that. So which gives an idea, especially for if you want a particular strength. Of course, maybe if you have the crystalline properties, moldable properties, mechanical properties. Yes. So there's a lot of in silico studies also there. This can be predict the composition of your materials, so that which can abundantly reduce your time and expenditure for involving random trial method. So yes, it is.
Any other questions?
Sir, the tissue engineering technology, how the way differ from crafting technology, sir?
Okay. So crafting is a broad term. Okay, so the crafting is a broad term. The purpose of the crafting is to mold the shape. Again, over the application stops there. It's the molding technology or crafting technology, and it may not be limited to the application oriented towards the clinical applications. It can be anything. Maybe even for any specific structures, or maybe prosthesis organs. Maybe if you take any complex structures not related to the clinic. Okay, so example I'm talking. So the crafting is a broad term which uses the engineering principles and dynamics which can be useful to design and shape the architecture of a particular product. But here in the tissue engineering, we use the technique to design and define the shape of a scaffold we're using, because that is going to be a base material where in which our cells is going to be seeded. So those are two different fields, but it has its diverse applications of crafting technique. But one of the applications we use that technique for molding as a 3D as principle. We are molding for developing of scaffold, which is one of the important triad element of our tissue engineering. Does it make sense?
Thank you, sir.
Yeah.
Any other questions? Sir, I think we are at the end of our session, sir.
Okay. Thank you very much.
Sir. Yeah, thank you, sir. Thank you for spending your valuable time with us, sir. So whenever you're coming to India, just kindly let us know, sir. If possible, we can have a session with you, our students directly, sir, because knowledge transmission will help the students to grow better, sir.
I would be happy to. I would be happy to help our students or young minds, because it's my pleasure and privilege, as I mentioned during the introductory. What I have a little knowledge which I've gained through the years. So it is in fact, it is a good platform to interact the students so that they can know the knowledge what's happening in and around the globe. So I would be very happy and to interact with the students, especially if they have any doubts or clarification or future perspectives on the research, especially when they want to venture into the tissue engineering. I'm always glad to help them.
So definitely, sir. Have a nice day, sir. I think you are on Eid festival is going on in your places. So have a nice day and enjoy the celebration, sir.
Yes.
Thank you, sir. Thank you very much. We will get you back to soon, sir.
Thank you very much. Have a nice day.
Thank you, sir.
Stay safe and stay healthy. Bye-bye.
Thank you, sir. Wish you the same. Bye, sir.